Welcome. In this video, we're going to talk about 4 codes that will kind of give us a build-up towards a discovery of the Hamming code. So when I first read about the Hamming code, I didn't really understand how someone could possibly come up with it. So through 4 codes in this video, the triple repetition code, the Ravenstein code, Liu's grid code, and Liu's star code, we're going to build up towards how someone might be able to think of the Hamming code. So let's start with the triple repetition code. So it's published in 1950 by Alt and is a code which sends the same message 3 times. It can correct 1-digit error and detect up to 2-digit errors. So let's play this game. If you've received the following code word and we're trying to use the triple repetition code with receiving this word, how could we do the error correction? So the idea is to look at how it's been repeating and notice any inconsistencies. So this column right here would have an inconsistency because it's not the same. And what you do is take the best 2 out of the 3. So if it only has 1 error occurring, the error has to be with this 1 right here. So the actual code word is this with the corrected 1 to a 0 right here. And the actual message is just the 5 digits that are here. So what the sender did is take the message, repeat it 3 times, and then when an error occurred, you're able to correct it by noticing the 2 out of the 3 have to be the correct choice for the message, and the one that's wrong is the third option. So apparently the triple repetition code was national secret at one point, that people were very sort of nervous about all of this information that was being transmitted during the time of World War II, and the knowledge of how to correct and detect these types of errors through digital signals was very new information. So I felt kind of humored by the idea that just taking something and repeating it 3 times was this national secret that had to be covered up by Alt until they were actually able to publish it at some point. So there's something else that we should always be concerned with when we're trying to design a code. What is the efficiency? So you'd like to have a higher efficiency. So we measure efficiency by taking the message length, so the message, what we were actually trying to send, versus the code word length in terms of what was actually sent. So it's kind of like saying, well, what was the penalty for trying to send this via the triple repetition code? Well, the penalty that we had to pay was 10 extra digits. So in terms of modern usage of coding, that's pretty terrible. It'd be pretty terrible if you wanted to send 1 gigabyte, but to send 1 gigabyte, you had to send 3 gigabytes to do that. That would be pretty awful. So there are better techniques. This is just our starting point, our very primitive starting point. Another way to measure the efficiency is you can take the code word length, so all of this amount here, and then subtract the number of check digits. So the check digits are anything extra. So all of these in this context are check digits because they're all extra. They're all extra to the message. These 10 digits are just added to make sure that the message gets across correctly. So what would the efficiency of the triple repetition code be? Well, it would be a 1/3 type of efficiency. Now, in order to solve Bhaskar-Hound's problem that came at the beginning of the previous video, we had to ask 15 questions and get an answer out of that. So I'm going to always take our efficiency out of 15. So we're having something common to compare it to in the context of that kidnapper problem. So our efficiency would be 5 out of 15. So we're going to now ask the questions that solve part 2 of the Puzzle Mad Kidnapper problem. So what this one said is now we're going to say Baskerhound does lie, and we are trying to figure out Baskerhound's number between 1 and 2000, but we do have 33 questions to ask. So there's a lie, 33 questions, a number between 1 and 2000. So what you could do is say, what is your number in binary 3 times? Well, we did that in example 3. So if you look back at the previous video, example 3 said, what's your number in binary? Via 11 questions. So you could do that 3 times. You could say, that's my first 11 questions, and then you could do example 3 again, and then example 3 a third time. Okay, so for all of these codes that we're going to introduce, building up to the Hamming code, we're going to give them a nice little ranking as well. So every code gets the efficiency according to whatever it is out of 15. Remember, we're always going to put them out of 15, so we have something to compare it to. So 5 out of 15 for the triple repetition code. And then you can give it whatever face you like or whatever quality you like. I'm going to give the triple repetition code the shocked face, because I was kind of shocked that the triple repetition code was national secret at one point. In terms of math quality, it's just not very good. I'm going to give it a half a star. It does something for us, but it's very inefficient. Okay, let's look at our next code. Our next code is called the Ravenstein Code. So this code was due to Mark Ravenstein, who apparently was witnessing an outreach event at McKernan Junior High School in Edmonton. And during the presentation, they were talking about the Hamming code, and they were talking about the triple repetition code, and they were trying to relate the two. And apparently, Mark Ravenstein put up his hand and said, why would you ever want to repeat things 3 times where you could repeat things twice and have one check digit to check which one of the two is correct? So from there, with a little bit of help, Mark Ravenstein published the Ravenstein Code. So let's investigate how this one works. So what you can do is repeat twice, like we were saying before. So 1 repeat and then a second repeat. And then what you do at the very end is you place a check digit so that the amount of ones together with the check digit is an even amount of ones. So if we want to count up those ones, we'd have 4 ones there, and then add the check digit, so plus 0 in this case, because there's no ones for the 0. And then the same thing with the other portion. Count up the number of ones, which is 4, and then add 0. Add the check digit at the end. And ask yourself, are these numbers even or odd? So these numbers here are even. That's an even number as well. 4 is an even number. So in this particular case, there was no error. Or you could also say that this is what the sender sets up to send away. The sender would have this message, would repeat it, and then would put one more check digit on the very end to make sure that it would get through correctly via the Ravenstein code. Okay, let's check one more. So counting the number of ones, in the next one we have 1, 2, 3, 4, so there's 4, and adding the check digit on the end, this time you would add 1. And in the next portion, I count 1, 2, 3, 4, 5, plus 1 for the check digit at the end. This time the check digit at the end is 1. So the first category, in terms of ones, is an odd amount, and the next we have 6, so that's an even amount. So in this scenario, the even amount is the correct one, and the odd amount is the incorrect one. Because remember, the sender always sets it up so that you have an even amount of ones together with the message and the check digit. So here, the message is ones, 2 zeros, and a 1. So that's how the receiver can do some correction. Okay, so for the next one, again, counting the number of ones, we would count 2 plus 0. And then in the next part, 3 plus 0. And then we would ask ourselves, is this even or odd? So 2 plus 0 is even, and 3 plus 0 is odd. So this time, the first part is the correct part, and the incorrect part is in that second portion. So the message is right here. Okay, let's do one more example. In this last example, adding the number of ones gives us 3 plus 0, and both of those are odd. So in this situation, the message is good, no problems there. The repeated portion of the message is good, but the thing that's throwing it off is the check digit. The check digit was an error. So the message that the receiver was trying to get is this, and the issue was that the rightmost check digit was an error. Okay, let's use the Ravenstein code to solve the Puzzle Mad Kidnapper problem in another version. So this time, Basker Hound lies, but we get 23 questions. Well, that's exactly enough for the Ravenstein code to help us out here. We can ask, what's your number in binary? And then ask, what's your number in binary again? That will take 22 questions. And then we'll have the final question, which is the rightmost check digit. So to get that final digit, we'd ask, in binary, are there an odd number of ones? Okay, so finally we want to rank the Ravenstein code. So our message length out of 15 is 7. So 7 out of 15. And I'm quite happy about this improvement. And in terms of quality, feels like we're halfway there. So I'll give it half the stars. Okay, let's explore our next code. So the next one is called lose grid code. So what lose grid code does is places the message in a 3x3 grid. You could use a different size grid, but for our purposes, we'll use a 3x3 grid. And then we place an additional check digit at the end of each row and at the end of each column. And the check digit, very similar to the Ravenstein code, is designed so that the total number of ones is an even amount. So let's go through and check each row and column to see if we have an even amount. If we've received these code words, let's try to do the error correction below. So counting up the number of ones, we count 4, and then we count 2, and then 2, looking across in those rows. And then now we'll look in the columns, counting the number of ones. What we get is 2, 2, and 2. So each row and each column check out to an even amount. So in this case, the message is exactly what's sitting there. There was no errors. Or you could think of this as exactly what the sender sets up before they get ready to send it away. Okay, let's look at another example. So in the example below, we'll count each row and each column for the number of ones that are there. So the first row, we count 2, and then 1 and 2, and then 1, 2, and 2. So the even ones are good. There was no error in those rows, so we'll give those a check mark, but there was an error in the second row somewhere because that should be an even number, but it's an odd number. So now we'll check the columns. So the first column here, working from the right, has a problem, and the others are good. So in this case, there's a problem in this column and in this row. So the problematic digit must be this one here. That's how we can do the error correction. So let's point that out. This one right here, that is the error. So the message would involve flipping that 0 to a 1. Okay, let's try one more example. So in the first row, we have 4, and then 2, and then 2, and then 3 and 2 and 2. So we'll give all the even numbers a check mark and the odd numbers an X to indicate that there must be a problem in this column. But there was no problem in any of the rows. So all these are good, good, good. There's a problem in this column, so the problem must be this final digit here. Let's remember that the check digit could be an errored digit as well, and this time it certainly is. So that one right there is our error. So in this case, the message is exactly what is sitting right there. That part didn't have any errors with it. So let's give our lose grid code a ranking as well. So what efficiency did we hit this time out of 15? Well, the message was 9 in length. There was 9 digits in the message. So my efficiency is 9 out of 15. So I'll give this the happy face again. I'm quite happy about that improvement. And we're doing pretty good. I think that in terms of the stars, this time I'm going to give 3 stars with the creative use of a rectangle to get error correction. So there's one more improvement that we're going to talk about to build us up towards the Hamming code. So that is lose star code. So this one is quite similar. We again use the geometric shape idea. In this case, we use a star. And what's going to happen with the star is there's more intersection points within your star. So when I saw this one, it really helped me understand how to solve, Basker-Hound's problem and where the Hamming code might be coming from. So what we do is we draw a star down on our page, and then on each intersection in the star, you send a message bit, a message 1 or a 0, and then you extend the line of each part of the star to have an extra check digit to make sure that that line has an even amount of ones. So let's go ahead and do the error correction on the star below. So if we check line A, we would check along here and we count the number of ones. So 1, 2, 3. So there's 3 ones on A. We'll write the 3 down. Already that's a problem. This number here is supposed to be even. Okay, now let's check line B. So looking along line B, we have 1, 2, 2 in total. So looking along line C, we have 1, 2, 3. So there's a problem on line C as well. So maybe we could stop there and think about line A and C, but we'll keep going just to complete the process. So on line D, we would count 1, 2, 3, and 4. Okay, so once we hit line D, we count a grand total of 4, and line E, 1 and 2 in total. So for line E, it's good, and the same with D and B. So the problem is on line A and on line C. So it must be the intersection between line A and C, just like the intersection with the rectangle from before. So that digit right here, that one is our error. Okay, so we're all ready to rank lose star code. So if we just get that onto our screen as well, what is the efficiency of lose star code? I'll let you pause the video now and think about that. Okay, so the efficiency is the message length. Everything on the star itself is a message. You get to make those ones and zeros whatever you like, and there's 10 of them. Plus there's 1, 2, 3, 4, 5 check digits around the outside. So that makes a message length of 10, an efficiency of 15. And I'm going to give this one the super smiley face because I was really happy to discover Lou's star code in my research, because it really led me to understand more about the Hamming code. And in terms of math quality, I'll give it 4 out of 5 stars. This is really good. It's actually almost as good of a code as you can get. The Hamming code is just a little bit better. In fact, some people call the Hamming code a perfect code because it is proven that the Hamming code is as efficient as you can possibly make a binary code that does one error correction. So we have a little bit of room to improve. In the next video, we'll explore what that's all about. So thanks so much for listening. We'll see you on the next one.